For the longest time, the mantra in AI has always been go deeper, right? Just stack more layers, throw more parameters at the problem, and somehow real intelligence will just pop out. But what if that's a huge misunderstanding? Today, we're diving into a really cool and kind of radical new idea called nested learning. And it suggests that the future of AI isn't about getting deeper, but about building smarter, more elegant structures that can learn at different speeds, a lot like our own brains.
To really get our heads around this, let's start with a question that you've probably felt yourself. Have you ever been talking to an AI, even a really smart one, and noticed it just forgets something you told it like 2 minutes ago? Well, that's not just a random glitch. It's a fundamental limitation. It's almost like these incredible models are suffering from a kind of digital amnesia.
And look, this isn't just some fancy metaphor. Researchers have actually drawn a direct parallel to something called anterograde amnesia. That's a real neurological condition where people can't form new long-term memories. As this paper points out, a large language model's knowledge is basically trapped. It's either in the immediate, super short-term context window, or it's part of that massive but totally frozen knowledge from its initial training. It can't make new, permanent memories from our conversations. It's literally stuck in the past.
So how do we fix this? Here's our game plan. First, we're going to dig a little deeper into this whole amnesia of AI thing. Then, we'll introduce the solution, nested learning. We'll see how it works with a pretty surprising example of learning at different speeds, explore this cool concept of a continuum of memory, and finally, we'll meet a brand new AI architecture that puts it all together, called Project Hope.
All right, first up, the amnesia of AI. The bottom line is, even with all their power, today's models are basically static. Once that giant pre-training phase is over, their long-term knowledge is pretty much set in stone.
This slide just lays it out so perfectly. Our brains have this amazing two-part system, right? We have an online phase for what's happening right now, and then an offline phase, like when we sleep, where we consolidate those memories and actually learn from them. Well, LLMs are just missing that whole second step. Their in-context learning is like a fleeting thought that just vanishes. It never gets written into their core knowledge base. They don't have that sleep-on-it moment, and because of that, they can't truly learn.
So, if the problem isn't just about stacking more layers, what is the answer? Well, this is where nested learning comes in. And it's a total paradigm shift. We're moving from thinking about flat layers to building with different levels of learning.
Okay, so what is it exactly? Nested learning sees a model not as one giant single calculation, but as a whole system of, well, nested optimization problems. The best way to think about it is like a set of Russian dolls. Each doll inside is its own learning process, and each one is running and updating at its own unique speed.
This visual just hits the nail on the head. Traditional deep learning is like stacking pancakes. You get more pancakes, but it's all just more of the same thing. Nested learning is like those Russian dolls. Every new level you add isn't just more capacity. It's a whole new learning ability, operating on a totally different timescale. It allows for a way richer, way more complex form of intelligence.
Now, to really appreciate this, we have to grasp this one key distinction. There's a massive difference between just memorizing something and actually learning it. The paper puts it beautifully. A memory is just a neural update, a reaction to some input. But learning? Learning is the process of figuring out which of those memories are actually useful and worth keeping. And that distinction is the absolute foundation of this whole framework.
Okay, I know that might sound a little abstract, so let's bring it down to earth. We're about to see how the very tools we use to train our models, the optimizers, are, believe it or not, secretly nested learning systems that have been hiding in plain sight.
And this leads to a kind of mind-bending question. What if the very things we use to train models, the optimizers we thought were just dumb algorithms, are actually learning systems in their own right?
Let's take a super common tool, gradient descent with momentum. If you look at it through this new nested learning lens, you realize it's actually a two-level system. You've got the outer loop, or the slow network, which is the model's main weights. That's where long-term knowledge gets stored. But then you have the inner loop, the fast network. And that's the momentum term. It's constantly and rapidly updating to keep track of what's happening right now in the training process. It's like a short-term memory just for the learning process itself.
The implication here is kind of profound. Your optimizer isn't just a passive tool. It's an active learning module. That momentum term is basically a little memory system that's learning and adapting to the gradients. This has been happening right under our noses the whole time, and nested learning finally gives us the vocabulary to understand it.
Okay, so if even our basic tools are secretly these multi-speed learning systems, what happens when we start designing AI with this principle in mind, on purpose? Well, this opens the door to an incredibly powerful new idea, a continuum of memory.
A continuum memory system, or CMS, is really the logical next step. Instead of this rigid, black and white distinction between short-term and long-term memory, a CMS creates a whole spectrum. You can picture it as a chain of memory blocks, where each link in the chain is updating at a different speed. This gives you a much more flexible and brain-like way of remembering and learning. And you can see here how this totally transforms a standard building block of modern AI. A traditional transformer has its attention for working memory, and then a single frozen block for long-term memory. The new architecture, which the researchers call HOPE, swaps that one static block for a full-blown continuum memory system, a dynamic chain of memory that can learn and adapt at all these different speeds.
Which brings us to our final section, Project HOPE. This is the architecture that was specifically designed to put all of these amazing ideas into practice and see what happens.
So at its heart, HOPE is a combination of two really powerful concepts. First, it has that continuum memory system we just talked about. And second, it has what's called a self-referential module, which is a super clever way of saying it learns how to learn as it goes. This is an AI that's not just designed to process information, but to genuinely learn from it.
But, talk is cheap. Does this fancy new approach actually work? Well, the results are pretty darn compelling. This chart shows how HOPE performs against other strong models of a similar size on a bunch of tough language and reasoning tasks. And as you can see, that nested learning approach gives HOPE a real, measurable edge over the competition.
The message here is just undeniable. Nested learning isn't just some neat theory on a whiteboard. When you actually build an AI with these principles, you get models that aren't just bigger, they're demonstrably smarter and more capable, hitting top-tier performance.
So, what's the big takeaway from all this? First, the future of AI isn't just about scale, it's about structure. Second, nested learning gives us this whole new dimension for thinking about that structure. Third, this new way of looking at things shows us that learning is happening in places we never expected, like inside our optimizers. And finally, it all leads to these incredibly dynamic, brain-inspired models, like HOPE, that can actually truly learn.
And all of this leaves us with a really crucial question for the future of AI. As we move forward, should our goal be to build models that are simply deeper, or models that are more elegantly nested? The answer to that could very well shape the next decade of artificial intelligence. Thanks so much for tuning in.